All right, so I am live streaming us, so we are ready to go. Marcus, again, do you want to share your screen?
Yes, working on it right now. Okay, I think that's okay. Good.
That looks wonderful. All right, I'm going to let everybody into the room, and when you start talking, I'll hit record. Our student volunteer, Demilula, if you want to take yourself off of video, there we go. Looks good, everyone.
Hi, Marcus. So, let's see.
Hello. Hi, Steve.
Hi, how are you? So,
Very good. How are you?
pretty good. So, let's wait for a few more minutes, and then I think people are coming.
Sounds good.
Oh, so the background is moving. I can see the spine.
Yes. It's moving. That's right.
You'll get remote arachnophobia, virtual arachnophobia.
Yeah, I was gonna say I have a couple of photos of spiders, but not too many. But if you don't like spiders, you might want to close your eyes in the meantime.
So I suggest we wait for 1 more minute because usually people come a little bit late. Just take 1 minute and then we can start.
Sounds good. I'm inspired by your background, Steve. So I'm gonna put my own MIT background here. You see, there's some sort of. You must be on campus, right? Or
No, I was at home for the last couple of months, but maybe hopefully later on, we actually need to have a weekly testing in order to go back to campus. So if I miss the testing, then I have to wait until I get the test, which is actually a good measure. So I think that we want to see if we also need to wait until the host come back so that he can start recording the sections. So let me check.
Mm-hmm.
So I'm the host right now.
Steve, it says you're co-host, so if you you can even start the recording.
Okay, okay. So we start recording. Okay. Okay, so maybe we should start. So it's our great pleasure to actually introduce our next speaker, Professor Marcus Biller from MIT. I think it requires no introduction. So yeah, as you can see the background, so we see a spider. So let's see what this is about with the by-inspired material by design using AI. So thank you, Marcus.
Thank you much, Steve, and Krishna, and everyone organizing this and inviting me. So what I'll do today, I will give you a little bit of an overview of recent work we've been doing, including some work we literally are just working on as we speak. So my students and postdocs sent me some really exciting slides and updates over the last couple of days and overnight. And I hope to have a discussion with all of you and engage in some fruitful deliberation. So my lab is interested in what we call matriomics, which is engineering materials across different scales. We begin to engineer materials, understand them from the molecular scale and nanoscale, and we are interested in engineering all the different levels: the scale of atoms, the scale of molecules, of assemblies of molecules, mesoscale structures, microstructures, all the way to the structural level, which is structure of a building or the shape of an engineering part, maybe. And we found this to be a very interesting paradigm to create very functional and very sustainable material solutions. And the backdrop to all of this really is that nature in its living world utilizes these kind of multi-scale engineering paradigms in pretty much anything it builds. And one of the best engineers we see in nature, or materials engineers we see in nature, is the spider. Here's a little photo. This spider is builds quite interesting webs, and is a very interesting animal that creates structures like this here, an orb web. But many spiders also build, actually most spiders build structures that are a lot more complicated than that. Those are three-dimensional webs. You see here one of the photos I took a few days ago of a three-dimensional web. And if you look closer into these three-dimensional webs, you actually see a lot of internal structure. In fact, this here is actually a three-dimensionally, an additively manufactured printed web of one that we have analyzed and scanned using three-dimensional laser tomography. And what you see is there's a lot of interesting structure in there. And this material, silk, which the spider produces, is used in a variety of ways to catch prey, to wrap eggs, protect prey, store prey, and of course, as a way to live, for the spider to live in. But these silk threads aren't only made used in nature to make spider webs. They're also used to build many other materials like tendon, for instance, skin, muscle tissue, cells. And in all of these different examples you find in nature, these hierarchical structures have a direct relationship between the property that we want at a certain level, the structure, and the process to get that property. And so unlike in an engineering system where you might have three relationships between structure, process, and property, in a natural system, a living system, you have these very intricate hierarchical cascades of these relationships. And that's interesting in particular because nature actually uses very simple building blocks to make all of these materials. Chemically, they're all made from, a lot of the examples I've shown you today are made from amino acids or proteins. And these create a variety of different functionalities like adhesives, spiderwebs, very strong, very tough materials, or sensing materials, cells, living materials, neurons. They're all made from these kind of simple building blocks. And nature uses this paradigm to create hierarchies also in other material systems like conch shells, for instance, nacre, where very simple ingredients, in this case being a very brittle and a very soft material, combine in patterns to create an overall, say, tough material or very strong material as a composite. And actually in these composites, what makes them special is that these defects or imperfections or combinations of different materials actually result in a strong or tough material. So unlike in engineering, where we usually at times we like to avoid defects, nature actually engineers defects deliberately into the structure to provide high toughness and high strength and other functional material properties in nature. Now, this is how we got into using machine learning or AI techniques to design materials in the first place, is to realize, of course, that when you look at a hierarchical system like a spider web or a composite or anything like this, you have patterns at different length scales and potentially time scales. And of course, CNNs, convolutional models, are very good in capturing these relationships. So in image classification, for instance, we classify an image, whether it's one type or another type or yet another type, by using filters, convolutions, to identify key features at different magnifications, essentially. And we use the same machinery, the same idea, to capture these cross multi-scale relationships that I showed you a couple of slides ago of living systems, to understand how inputs and outputs and structure relate to function ultimately. The other thing that we've been doing recently, in addition to actually just capturing relationships and using it for optimization, is also to use methods that allow us to synthesize material designs using neural networks like autoencoders that are very powerful in going. This is a picture of a spider web that we can try to understand and code into a reduced set of variables, latent space, and then create either the same structures, or more appropriately for engineering, of course, create structures that have desirable features or that fit on a certain geometric domain that we can utilize for design, and then maybe 3D print, like I've shown you in the very beginning, this three-dimensional spider web we've made in the laboratory. So these kind of relationships are abundant in nature. And so I'm going to show you a couple of case studies. First one is to systematically analyze how hierarchical structuring results in a toughening behavior. We've shown that by utilizing these soft and stiff material combinations, we can create a rising R curve behavior, which is to say essentially that if I have a crack in the material and the crack begins to spread, as the crack spreads in the material, the toughness increases. In other words, it becomes more and more difficult for the crack to actually propagate. And that's a very desirable property because it means that cracks can hopefully arrest and they don't move further in the material. And so we can utilize these hierarchical structures to actually create this rising R curve behavior, which is seen in nature. Now, the initial work we've done is essentially looking at a lot of natural designs like in nacre and bone, in many other structures like that, analyzing their relationships. But of course, we'd like to have an opportunity to design hierarchical structures from scratch with certain desirable property. And so this is how we began to use these convolutional models to essentially relate a geometry, a pattern of combinations of stiff and soft materials, which you can kind of see through this this design space here, which is quite significant. So if you have in a small problem like this, you already have 10 to the 20, 10 to the 100 combinations very easily, which would take millions of billions of years to actually do with brute force computation in terms of calculating all the different combinations. And so we began to think, can we utilize machine learning techniques to actually capture this and kind of treat this design problem like a game, like in Go, for instance, a few years ago, chess and many other problems like this can be very effectively solved by using these AI algorithms. And so we formulated this problem of designing a composite of two materials or more, actually, considering materials as a pattern problem to then optimize the pattern to create an optimal solution for high toughness or low toughness, or even dialing in particular toughness values. And so in the beginning, we create a training set using finite element modeling or other multi-scale methods. Could be a molecular dynamics simulation as well, or particle simulation to relate pattern with features. And then the machine learning algorithm will relate these patterns with the features and hopefully be able to learn the relationships in this flowchart. We run the code, label the data set, run the machine learning algorithm, optimize the model, create, in this case, in the first simple example, I'm going to show you a classifier, which then we can use to extract probabilities for predictions for designs that the model has not yet seen, and then go through an optimization procedure. So the first test we've done is actually to see whether we can, in fact, accurately relate patterns with mechanical features like toughness and strength. And in that paper in Extreme Mechanics Letters from a couple of years ago, we shown that this, in fact, works really well. And we have actually taken a smaller system where we can do brute force calculation and shown that, in fact, the agreement between the designs from finite element versus the designs with extracted from the machine learning model agree very well. And so we'd be able to capture the essential physics of fracture in these kinds of systems. I've also expanded this then in a follow-up paper to predict the behavior of algorithm systems. In other words, we use smaller building blocks to build bigger building blocks to build larger building blocks, right? So exactly like the way nature does it in the case of silk or other materials. And these, becomes algorithmically a very similar problem, of course, because the method still is looking for patterns, which is what these convolutional models can do very well. So in other words, we can quite very easily optimize and adapt the model to predict for hierarchical designs, and works really well. One of the features that we're very excited about is then to take these predictions from the machine learning model, the optimizations, say for high toughness or low toughness, and then use 3D printing additive manufacturing to actually make these composites in the laboratory. And so this is something we've done recently and tested them and confirmed the prediction. So this was sort of the beginning how we moved into that field. And since then, we've done a lot of work in looking at optimization algorithms, especially coupling the deep learning model with genetic algorithms and really trying to simulate nature, right? Nature's evolution works in that same way where mutations are made, are created, and the performance is assessed by nature through the test of real life, essentially, of how a spider survives, or how a nacre shell survives, or how animals do in their ecological niches. And the genetic algorithms, we can do similar things for composite design. We can optimize distributions now using the machine learning model as an evaluator. The advantage being, of course, that these evaluators run much more quickly than a finite element simulation or molecular dynamics simulation, so we compare them. One nice feature about this is also that we can use a sort of reinforcement approach to this as well, where we can enrich the data set, the training set, and improve the model as the optimization runs if we end up detecting that a model is not as predictive as we want it to be. So we can always go back to the ground truth and augment the data set, because we have essentially the ability to run, of course, another finite element simulation or molecular dynamics simulation to treat the model and enrich the data set. We've done this for a lot of different systems, including not only composites at macro level or micro level, but also for graphene, for instance. This is a study we've done recently on distributing nanoporosities in graphene and basically minimizing the stress concentration, which is typically the design feature you want in a model where you want to increase toughness, and works really well for a variety of different systems. So the other really interesting thing, of course, about fracture is that what you've seen so far was essentially taking a microstructure and relating the microstructure or different microstructures to a feature through convolutional models, essentially combined with a genetic algorithm. But one important feature of fracturing is actually that it's a multi-scale problem, but it's also a problem where the path is really important. A lot of times in engineering, we want to know if you have a crack propagating, we want to know how does this fracture actually move. So on the left-hand side, you see a fracture in silicon, for instance, and you have some really important microscopic features. On the right-hand side, you see a fracture moving in a polymer. And the question always is, how do we prevent fracturing from happening, and how do we control the stability or instability of fractures from occurring? And this is widely important for many there, from fragmentation, explosions, impact loading, to biological loading, stretching, cyclic loading, earthquakes. These kind of dynamical phenomena are critically important for engineering and science. So we set out to think about whether we can actually train a machine learning model. Now, in this case, a model that can actually capture the history of images and predict the future evolution of images using the LSTM model to utilize molecular dynamics simulations. In this case, it could also be finite element simulation as an input, to understand the history of how microstructure, of how the atoms are arranged in the material, relate to the evolution of a defect, of a crack over time, and then be able to predict the evolution of cracks for a new design, right? And then predict the crack dynamics in that sense without ever doing a finite element or molecular dynamics simulation. And so we followed a similar pattern in setting the model up, in the sense that we have MD simulations to provide the physical ground truth, the AI model to learn features from adequately labeled data, and then essentially solve that problem to go from an initial crack in a material to predict the evolution of this crack without running the actual MD simulation. And the way we formulated this problem is essentially by running long MD simulations, a large variety of MD simulations for different input crack sequences. We extract the patterns and then learn these progressive crack sequences from the crack features, and then able to classify using classify layer which atoms or which bond between atoms is going to break. And this gives us the ability to predict the evolution of a crack, or in other words, make a movie of the physical evolution of defects or cracks in the material. This, I think, has applications in a lot of different settings. We've done this now for brittle fracture and ductile fracture, working on some diffusion problems, and I'll show you later on some protein folding problems. But obviously, the method can be applied as well to dislocation dynamics, or grain boundary evolution, or maybe a cyclic loading, fatigue loading conditions. So there's really a lot of different applications where a model like this could be used. And what is remarkable is that this model, the paper was published just a few months ago, earlier this summer, is able to capture very accurately the microstructural dependence. In other words, what angle the crystal has with respect to a reference point. The crack will go in a very different dynamical setting and have different kind of branching dynamics. So on the left-hand side, you actually see these variety of simulations. You can see that depending on how you orient the crack either will not propagate, or will propagate in a certain angle, or have certain branching features. And the model is very accurately able to predict these kind of branching features once the machine learning model is trained. And now, why does this matter? One application that we've used this for is, again, the materials design problem, where you can now begin to design gradient materials. In other words, you don't just have a single, orientation of a crystal, but you have many different grains oriented in a gradient with slightly changing orientations. And that's something, again, we look to nature a lot, as you know, in my research. And in many natural materials like bone or bamboo and others, enamel, we had just a paper on enamel and teeth a couple of months ago, actually last year, with Cooper Gilbert. These materials have gradients a lot of times, and so what you see on the right hand side in this movie actually is the prediction of the machine learning model for gradients like this. In engineering, a lot of times we're dealing not necessarily with gradients, but we're dealing with grain boundaries, like twin grain boundaries, and we have done a lot of tests actually how predictive the machine learning model is. And in fact, we've shown here that even though the model has never seen these kind of grain boundaries, we can accurately predict crack branching or crack arrest actually in these systems. So this is very, very exciting. Not only can this be applied to simple brittle materials and model materials, but it can actually be applied to also more complex materials like graphene fracture. And graphene is obviously chemically much more complex than the perfectly brittle material, which is a hexagonal lattice material we've shown in the previous examples. It can also very accurately describe the relationship essentially between microstructure and branching and other features of the crack. So this is very exciting, and that paper is currently in submission. So shifting gears a little bit, I want to talk a little more about proteins now. So this, I think, is an exciting moment in time where we can begin to, as I've shown you with the two examples I've talked about so far, complement physics simulations, physics-based multi-scale modeling to create training sets and use a variety of machine learning models to predict the evolution of defects, of cracks, assess design solutions very quickly, and then move this into 3D printing and additive manufacturing with really interesting feedback loops. But the protein problem is something that we're very interested in. I've worked in proteins for many years, almost 2 decades. And in proteins, I'm particularly interested in the relationship between the protein sequence and the structure, but really interested in the feature or the function of this protein. So in other words, we want to go from a protein sequence, like an amino acid combination, into a feature like a mechanical property or biological property or a certain structural component, a microstructure, which then can be linked to a functional feature in biology. So these kind of relationships is what I'm going to talk about for the next couple of slides until the end of the talk. And we have a variety of efforts in this field, talking about structure function as well as musical coding. We do have developed a methodology to actually treat this protein design problem as a language which works through frequencies. Identified that each of these DNA letters translate into amino acid codes, that 20 of them has a unique audible spectrum of frequencies. And so we can actually formulate the problem of designing materials not only as a geometric problem, but actually as a problem in an audible space. So what you hear, I think you can hear a little bit of the sound in the background. When you think about musical composition, it actually follows a very similar paradigm as the composition of materials, if you wish. So, classical music, you can break it down into basic waveforms of a sine wave. You think about modulating a sine wave to create the sound of different instruments. You can create multiple tones, you can create melodies, riffs. And of course, sound of an orchestra is really the combination of many different rhythms, many different melodies played against each other and competing. And in a similar way with a material, you can see the analogy. You have the amino acid sequence, you have the assembly in different structural levels, and to create this combination of coding. So this actually can be utilized, this formalism can be written down mathematically rigorously, and we've done this in a recent paper in ACS Nano, published that last year. We have a couple of follow-up papers this year. You can take a look at this, where we have developed a formal coding mechanism to really translate physics-based certification techniques, going from a protein sequence into a protein structure, coding the structure, the three-dimensional geometry of the protein into an audible space as a signal you can hear or you can process, and then utilizing these codings as a very effective way of coding protein sequence, structure, and function in a data set, essentially, that we can then use for machine learning application. And one of the applications for this is that we can classify different proteins, of course. We can also design new proteins by essentially composing new music. Of course, we can do that as a human, but we can also ask computers to generate new protein designs following certain constraints using similar methods as I've shown earlier, using actually genetic algorithms or other optimization schemes to couple a machine learning model prediction with feature extraction and then arriving at an optimal solution or targeted solution. And we've done this for a couple of cases, including this protein here that you see on the screen is one that we have designed by creating new music that speaks the language of how proteins are designed in both sequence and structure, different length and time scales. And then we made that protein in the laboratory. So this is, I think, the first protein that has ever been made by composing a song, basically, and then translating that song back into an actual physical material structure. So this is very exciting, and I think this direction has taken a lot of new avenues in my lab. One is to look at sort of classes of proteins, like collagen, for instance. I mentioned in the very beginning, I showed you pictures of tendon and bone. These are proteins that are extraordinarily important in the human body. Collagen is a triple helix, like a rope, and it follows a particular pattern, again, a pattern of design that nature uses to make these kinds of proteins. What we've done here is we use a database of various collagen molecules and their physical property. And the goal is really to go directly from an input sequence of an amino acid sequence of various collagen designs, and relating this directly with a function, a property, a feature, in this case, the thermal stability of this protein. And this allows us then to really do optimal protein design very, very quickly. The model works really well. You've seen the training performance is very good. This is a relationship between the machine learning and the exponential correlation. And what really begins to have a lot of really interesting and fun aspects now when you have a model, and you can very quickly with this model assess mutations. In other words, you can go in and say, let's design hypothetical sequences of collagen proteins that nature hasn't invented. And you can make systematic changes, studying the disordering in the sequence design, make mutations, and add hydrophobic, polar, different charge residues, which would be very costly, of course, experimentally to do. It would take months for each of the designs. And it would also be very costly computationally. If you would have run a molecular simulation, even very rapid GPU-based simulations are going to run for quite a while to do that. So what the machine learning model has enabled us to do is to sort of derive some really interesting new physical insights into the relationship between sequence and property, and then make some of those designs in the laboratory. This is work with David Kaplan at Tufts University, whom I've worked with on anything from silk to collagen to SELPs to elastin, together with Tony Weiss for many, many years. And this is our latest sort of direction we've been pursuing. And some of those proteins are, this is very recent results, not published yet, but we're going to be submitting that paper very soon. And we have experimental studies that complement these predictions on the machine learning model. So this will be a very exciting combination. So a lot of this work in my lab has been to go from sequence to function. But we also have an effort in a collaboration with a team at IBM to develop a folding model that can actually go take the intermediate step. Because for many proteins, of course, we have structural information, either in a data bank or from other folding techniques, or about collagen, we know a lot about the geometry. But many other proteins, especially the ones we want to design from scratch, de novo proteins that nature hasn't invented, one of the methods we've utilized is the musical coding, the sonification coding that I talked about earlier. But we want to be more directed and actually be able to predict specifically the structure, and then from the structure, using these classifying techniques to relate structure to function, to build a whole picture, a whole pipeline of flow going from a sequence to a desirable mechanical or optical or biological functionality. And so in this model here with my colleagues at IBM and my colleague at MIT, Benedict Marelli, who's an expert in food coatings and food science, we're actually trying to develop proteins that are eligible to provide sustainable solutions as food coatings. And so the design space is a very complex one. We want to find a protein that has antimicrobial properties. We want to find a protein that has creates enough porosity at the mesoscale level to allow for gas exchange in the coatings around food. So Benedetto, my colleague who works in the food science of this project, is an expert really in understanding how to create coatings out of proteins around fruit like strawberries. And so you can imagine, instead of wrapping your strawberries in plastic, which creates a lot of pollution, you can wrap your strawberries in silk or silk-inspired protein, or maybe future proteins we're about to design using this AI technique. And so this model that we're developing is on that pathway. And we have a first model version published, this multi-scale neighborhood-based neural network model, which allows us to fold protein without any templating and go directly from a sequence to structure. And we're kind of building and growing the protein really as it is created. And we've done this for a couple of small proteins. Some of those results are in that Extreme Mechanics Letters paper that we published earlier this year. We validated that not only against simulations, so we've basically done the brute force simulation of folding the protein in an explicit water model, but we've also synthesized these newly designed proteins in Benedetto's lab to measure their structure and found the agreement between prediction from the machine learning model for folding, the features extracted from the mechanical simulation, molecular dynamics, as well as the experimental validation, and also tested, of course, against other competing folding methods as well. So this is very exciting, and we're beginning to kind of move into the direction of designing proteins from scratch using this method. The latest aspect that we're incorporating into these relationships are to find better ways of coding the protein geometry, including a sequence, of course, but also including geometric features through graphs. These kind of protein design problems using graph representations, I think, are one of the most exciting directions, which, as you can see, are quite a few labs around the world are picking up in proteins. And we're using this specifically for designing proteins for structural, mechanical, and other biological functionalities and providing an end-to-end prediction. So we developed the method to transform essentially a protein into a graph representation, and then hopefully being able to relate these graphs with mechanical features. And so, you go from a protein to a graph, and you add features to that, like mechanical signatures. And one of the signatures we're looking at particularly are vibrational signatures. And what I've shown earlier in the sonification work, we know that protein coding is intimately related to the biological function through the way proteins move. And it's something that a lot of times is neglected. In the description of protein, you look at a protein picture, all the times you see an image, a static image, but actually, of course, proteins are continuously moving, and these motions are critically important to describe the function. And we had a recent paper in Cell Matter where we have shown actually at the motions of the COVID-19 pathogen and mutations thereof in different types of coronavirus proteins in the spike of this virus are directly related to epidemiological data like infectivity and lethality of the virus. So these motions are critical. And so with IBM, we're trying to use these graph models to relate not only static properties or folded geometry, but their dynamical motion properties, which we know relate very closely to functional features. And so we have some initial results that are very promising. We can predict the normal modes of proteins directly from the sequence through the graph neural network model and predict these modes of deformation, in other words, how the protein actually moves. And that we know has immediate implications for a lot of biological functionality. So this is something we're currently working on and wrapping up our first paper hopefully soon. The other thing that we've been doing is, a lot of times we think about coding geometry in these proteins using, say, contact maps, which is something that a lot of the protein folding methods that you have seen in other presentations or in the literature, including the deep mind algorithms for folding, utilize. And we've been trying to see whether we can identify an algorithm to move directly from a protein structure represented in a neighboring map to a geometry in three-dimensional space. And so this algorithm, I think, is very important for a lot of machine learning applications because we may be able to predict a contact map from the sequence as an immediate step and then move this contact map into a three-dimensional geometry. So my student, Kai Jin, has developed an algorithm for this, where we can go directly from these contact maps and kind of reverse engineer them, reverse code them, and create a dynamical folding algorithms. Again, we're interested in the motions in particular. And so what you see here is the actual folding process simulated by sweeping through these contact maps and using them as a constraint to build the protein model. So this is very exciting to complement a lot of these other things I've talked about, and we're working on trying to mimic these natural folding processes, the evolution. So you see that we go from a static picture, right, to more and more understanding not only a static picture, but also the evolution of pictures. Just like in the fracture example, we went from looking at relationships between microstructure and toughness to moving to the point where we can actually predict the evolution of cracks in time. And the same thing for protein folding. We're looking at the dynamics of how the proteins actually move. And that's incredibly exciting to complement. And this is my last two slides. For me, as somebody comes from the material science world and looking at biological materials and proteins, I'm extremely excited to use machine learning in two different ways. One is to kind of provide a bridge to complement the multi-scale scheme we already have, like on the top side here, The bottom is really something that, especially for the protein folding, the end-to-end folder we're developing right now with IBM, it really is going to be an end-to-end model where we can actually replace, in some sense, this multi-scale scheme that we have. And of course, we built the training set a lot of times from these multi-scale simulations, come in with experiment, but we can build them from scratch as synthetic data sets, have the ground truth essentially available, but complement them very nicely. All of this really comes together to me I'm interested in the fundamental function of materials, but also interested in designing and kind of improving on nature. If you think about the overarching challenges of today, one of them is sustainability, where you want to build materials that are more sustainable, like the food coating project with IBM. I think is a great example. Instead of using plastic, we're using proteins. But to design a protein for a particular mechanical and maybe diffusion property is incredibly challenging. We need to solve this multi-scale patterning problem. These kind of problems are not tractable yet, at least using conventional physics simulations. So maybe quantum computing will allow us to move faster in the multi-scale scheme in the physical sense. But in the meantime, AI, machine learning, is incredibly powerful to describe these dynamical evolutions, as I've shown you a couple of examples, and we're excited to apply that. And just as a little note, if you're interested in this, a little more, I teach a course every summer, including this coming year in June. If you're interested in this, sign up for it, or take a look at the website, or email me if you have questions. We do a 1 week long boot camp and kind of learning how to use machine learning in these design problems. And I think it's a lot of fun. A lot of students enjoy it, and participants from industry, students, postdocs. I look forward to having some of you there as well. And with that, this is my final slide, actually showing you a three-dimensional spider web, but this time not generated by the spider, but generated by GAN. And I think this shows the potential of really learning from nature in an entirely different way by replacing kind of learning how insects and other microorganisms or bacteria maybe build life, and mimicking that in the process of creating bulk materials or construction materials or building materials. I think is a very exciting opportunity for sustainability. With that, thank you very much for your attention.
Thank you, Marcus, for the very comprehensive and inspirational work. So we have one question from our co-chair, and also the audience. If you have questions, please feel free to leave it on the chat. So Chris, maybe I just read it out on your behalf. So Marcus, can you say something about how you select the feature for the multi-scale fracture problem with machine learning?
Yeah, so the features, in learning is very simple in this case. At least in the brittle fracture problem, you have essentially a material that is broken and that's not broken, right? So we have a simple map that's basically a white pixel and a black pixel, and the black pixel is indicating in each slice whether the crack has actually propagated through that slice and where it has propagated through. So that's the feature. And we, as I've shown earlier, we slice the image and we predict from these previous images the next frame, and we can then reconstruct essentially what looks like a movie, which is sort of what comes out of a finite element or a molecular dynamics simulation, which are frames of the physical state of the system. And that works really well. And we've applied this to not only the things I've shown here. We have a couple of new case studies where we went into other kinds of materials to see how general a method is, and the method actually works really generally well in terms of capturing a lot of different features and a lot of different microstructures, a lot of different molecular geometries of materials.
So if I can just add, so I guess this is all with CNNs. So have you sort of extended that down? If you try to look down at molecular scales, also have you
No, these are all molecular. Actually, this is all based on MD simulations, so it's atomic resolution in this case. Yeah.
Okay.
Yeah, and these are LSTMs, so we use LSTMs for these models.
So
in the beginning, the first part where we looked just at classifying a microstructure, that's based on CNNs, but then the time history, of course, we use a different model for that. Yeah. But it is atomic resolution. Now, what we do though, just to clarify, when you develop a model and you train it, you could pick an atomic resolution basically in the extraction. In other words, take an actual atom position and either fill that or not, right? Or bond that's broken or not. What we have done a lot of times, we have smeared out the resolution, essentially taken an average over a couple of atoms to come up with an effective model. But the original data is, of course, based on the MD simulations. But each pixel might represent more than just a couple of atoms. It might represent 5, 10, 12 atoms, depending on how big we make that. But it's flexible in terms of how we can put that together. Yeah.
So I think we still have a lot of questions. I also have some questions I want to ask, but in the interest of time to move forward, I will recommend that we move the discussions of this talk in the discussion board so that we can move forward. But let me thank the speaker once again, Marcus. Thank you for your time and a wonderful talk. Xun, are you here?
Yes, I am here.
Okay. Let me take the opportunity to save some time by start introducing our next speaker. So our next speaker, Xun Huan, is actually from University of Michigan, and then he will talk about optimum sequential Bayesian design of experiments using reinforcement learning with policy gradient. So thank you.
Great. Thank you very much for the introduction, Steve. And thank you, Steve and Krishna, for organizing this session and having me here. So my name is Xun Huan. I'm assistant professor in mechanical engineering at the University of Michigan. Today, I'm very excited to share with you some of our recent work on optimal sequential Bayesian design of experiments using reinforcement learning with policy gradient. I do want to point out that this work is spearheaded by my PhD student, Wang Gang Shen. So experiments in engineering science in general, they typically are very expensive. They can be quite time consuming to carry out and perhaps very delicate and intricate to set up and to perform. So for example, here are some of the experimental applications that I have been working with. Here is a picture of a combustion setup, combustion experimental setup from Argonne National Labs. In the middle here is a collaboration actually with Dr. David Kawabe in our department to design experiments for learning about properties of new batteries. And on the top right here, these are human subject experiments in collaboration with Dr. Kathleen Senko, where we are trying to use these mobile sensors placed on the different patients to learn about their physical capabilities, which is very useful for physical therapy and rehabilitation type of applications. So all these different types of potential experiments, they are very expensive. So it is often worthwhile for us to sit down and think about the design questions for these experiments, such as what conditions and settings should we do these experiments, what quantities should we probe in the system, where and when should we take these measurements, how many experiments do we need to do, how much data we need to collect in order to achieve some level of analysis. Okay, the particular type of experimental design approach that I'm going to focus on are these simulation-based or model-based optimal experimental design. And what do I mean by that is this is in contrast to some of the classical designs of experiments like space filling designs, uniform designs, latent hypercube, which do not require us to have a model that describes the underlying physical process. But often we do have good models to describe them. So for instance, in this case, this is a simulation model that we have, or I have worked on previously, that looks at a turbulent combustion process inside a scramjet engine, so for a hypersonic aircraft there. And with these type of high fidelity, accurate models, physics-based models, we can then think about taking advantage of these with this underlying physical knowledge to further guide the designs of experiments so that we can get more value, more information out of probing the systems while learning them. Okay, furthermore, I'm going to focus on the design of multiple experiments that can be conducted in sequence, one after the other. So this leads to the sphere of sequential experimental design. A big part of experimental design literature for sequential design focuses on greedy or myopic design strategies. And what that means is that we can design optimally, but for the next upcoming experiment only, without needing to worry about what happens afterwards. So kind of just do one experiment, design for one experiment at a time. Now, when you do that, potentially we could be missing out a lot of value by not planning ahead. So this, the greedy design do not have this element of look ahead, of thinking what would be the consequences or effects in the future experiment if I do something right now, if any. A optimal sequential design formulation would need to try to account for that. And there is work in formulating these optimal sequential design problem, but trying to solve them is extremely challenging. So the intuition that you can think about is we'll need to try to simulate all the different possible scenarios going forward, what would happen into the future. So that becomes very, very expensive, often prohibitive to try to tackle. Now we looked at some of these formulations and looked at some approximate dynamic programming algorithms to try to find numerical approximate solutions to them. And we saw some good results, but one thing that I want to point out is that they're very, very computationally expensive. So in our presentation today, what we're trying to do is to take a look at some of the reinforcement learning techniques that can potentially offer some computational advantages compared to our previous observations. Okay, so let's formulate our problem. We're going to model this entire problem using a partially observed Markov decision process, or POMDP. What we have here is we're going to look at the design of a finite number of experiments. So it's a finite horizon problem where the experiment index k goes from 0 to n minus 1 for a total of n experiments that we're interested in designing. These experiments, we're going to assume we're interested in learning about some model parameters. So these model parameters of interest is denoted by theta. So you can think them as, let's say, the Young's modulus in a new material that you have invented, or maybe the activation energy in a chemical reaction that you're trying to understand better, perhaps the diffusion constant of a contaminant diffusing out in a new medium. So all of those parameters, we're going to assume we're interested in learning those parameters from doing the different experiments. So we're going to, in general, they're going to be continuous random variables. So that's our theta. Then we have a state variable xk. So this is the state after k experiments have been conducted at the k stage here. So the state variable is in general some very comprehensive variable containing all the information that we need to make all subsequent design decisions in an optimal manner. So very comprehensive in principle. So how we're capturing them here is that first we have K, which experiment we're doing right now or have done. And also this is a belief state component, which describes the state of uncertainty that we have about the parameters of interest, the theta, that we want to learn from doing the experiments. Then we have a physical state component, xp here, which is any other non-uncertain variables or parameters, but also needed for making all the design, experimental design decisions. Then the design variables, also the actions. So we have here, so action of deciding what experimental design to adopt. So that's denoted by dk. So that's the design for the kth experiment, which in the sequential context then is really coming from the output of a policy pi that will tell us what is the best experimental design to do given the current situation or given the current state xk. So sequential design by definition, it's supposed to be adaptive. So you do the first experiment, you already learn something from that, and you can take advantage of that newly acquired information right away to update the design of your next upcoming experiments. So we're really now looking for an optimal design policy tied here. The experimental observations are denoted by YK. So they're in general the things you measure from the experiments, and they are noisy measurements. And then we also have a state transition function, this curly f here, which governs how a state variable xk with the experimental design that we just did and the observation from the experiment together then transition or update into the state at the next stage at k+1. So overall, the flow is as follows. We start with some initial state x0. And then we would have a policy, and the policy would say, under this x0, you should do this experiment. So that's the d0. And then you do the experiment, you get some observations from them, that's the y0. And then you combine all of these together to update it to the next state x1. And then you continue to design for the next experiment, experiment 2 here, and so on and so forth. Okay. But it's unclear right now what exactly should be the state. So let's talk about the state and the state transition a little bit more. And the most crucially is the belief state part, because we want to be able to describe the uncertainty on the parameter theta that we're interested in learning about. So we're going to represent the belief state and also the transition of the belief state using a Bayesian framework, Bayesian analysis framework here. And this works out very naturally. So let me explain what I mean by that. Imagine we just finished our kth experiment. And then with respect to that kth experiment, we would have a prior probability density function on the random variable theta, the parameter we're interested in. So that's this f of theta. So you can see everything it conditioned is not including the kth experiment, but everything we have done before that. So this is the prior with respect to that kth experiment we just did. So this prior multiplied by a likelihood function and divided by a Bayesian evidence, or also the marginal likelihood, then we get to the posterior PDF for theta, now conditioned on everything and up and including now the kth experiment that we just did. So dk and yk are also included. So you can see now this, you can view the prior and the posterior as the belief states, and we just transitioned from the kth belief state to the k+1 belief state. Pictorially, you can think it like this. We start with some prior on the parameter theta. We do the first experiment, then we can do Bayesian inference to update it to a posterior on theta. Then we do the next experiment, then we update it again to the next posterior on theta, so on and so forth. So the sequential Bayesian inference is a very natural framework to describe these belief states in a comprehensive and rigorous manner. Now, one just quick note here. Here I mentioned that the belief state is some characterization of the Bayesian posteriors. So what I mean by that is it doesn't have to be the PDF of the conditional random variable theta conditional everything here, but rather it can be, let's say, the CDF if you're more, if it's more advantageous to work the CDF instead. It can be the characteristic function for the random variables. It could be the moment generating function. It could be sufficient statistics or any other way to try to represent these posterior random variables. Okay, great. Now we want to find an optimal design policy. So we need to then think about what is it that we're trying to accomplish in these experiments so that we can define some reward functions or utility functions to assess how good or bad of a job we're doing. And to do that, the experimental goal, briefly mentioned before, is that we're in here, I'm assuming we're interested in learning about the model parameters theta in the physical systems. Then we can define state reward or utility here. And this is the immediate reward for doing that kth experiment. And this could be as simple as the negative cost of doing that kth experiment. Then we also have a terminal reward or utility, and this is After all n experiments have been completed, we need to assess how good of a job did we do in learning the parameter theta. And in this case, we're going to use the information gain, which is the Kullback-Leibler divergence between the final posterior after all n experiments have been completed to the very initial prior before any of the experiments have been carried out. So that's the terminal reward there. Now, before making the problem statement for this sequential optimal experimental design problem, I just want to maybe make some remarks about the attributes and some of the challenges of our problem setup so far. First of all, we do have a model-based problem because we do have the capability to simulate and predict what would happen in the next experiment. And that's thanks to a physics-based model, a predictive model we have together with the Bayesian inference setup, there. Second is that we have a planning problem because we have the model and also the reward function. So the problem is about solving or planning for an optimal design policy. We're dealing with finite horizon, finite number of experiments, which makes this problem a little bit more challenging than infinite horizon, since now we have to keep track of the policy at every different experiment, since they could potentially be different. So there are more things, more policy functions to keep track of. Then we have an infinite state space in this problem, and that can be understood from that because we have a continuous random variable theta to represent the theta. So to represent the belief state of a continuous random variable, one possible way to think about it is to use its probability density function, which is an infinite dimensional entity. So this is in contrast to a discrete random variable. Then you can represent the probability mass function for discrete random variable use a finite dimensional vector. But in this case, we can't. It's a function. So that also makes it more harder. Then we also have continuous action space and observation spaces. The belief state part where we're trying to capture general non-Gaussian distributions. The transition function involves performing Bayesian inference repeatedly when we need to do all the different simulations. And they would also entail the expensive, generally expensive Fourier model simulation, so like the physics model to simulate them. The reward function is an information theoretic metric, so it's the KL divergence. And estimating the KL divergence for continuous random variables where you don't have explicit probability density functions for them is not a trivial task either. And lastly, the policy that we're trying to learn here are actually mappings from these, let's say, these PDFs of the belief state represented as PDFs as an example to the reals. So then these policies are actually functionals. So they're mappings from function space to the reals, and even more challenging there. But nonetheless, let's take a look how we tackle this problem. So here is the problem statement. So I'm going to call this the sequential optimal experimental design, or SOED problem. So we're going to optimize something. We're going to optimize our objective function. And that objective function is this big U of pi here. So this is the expected utility evaluated at a policy, a potential policy we're considering right now. And this objective is the sum of all the stage rewards plus the terminal reward, where the design decisions for all the experiments need to follow the particular policy that we're considering right now. And since we're designing all these experiments, we haven't done them yet, so we do not know what will be the actual measurements or observations from these experiments. So we also need to have an expectation, conditional expectation outside, taking the expectation of all the observation variable conditioned on the policy that we're evaluating right now. Okay, and so we want to maximize this. So we want to find the optimal policy pi star that maximizes U of pi, and also satisfying the constraints from the transition function, as well as any additional design constraints that we may have or we want to impose. All right, so how do we solve this? One possible approach that we explored previously is to turn this problem into a dynamic program. So we can leverage Bellman's principle of optimality and write an equivalent expression for the same problem through the set of Bellman equations. So these value functions here. So the V is the value function at the kth stage, evaluated at a current state. So this you can think as all the best remaining value you have for all the remaining experiments. So it's the max of expectation of the state reward plus the same value function, but now starting from the next experiment, k plus 1. So it's a recursive definition. The approach we looked at in solving this is to use value function approximation, a type of approximate dynamic programming technique there. And the idea is simply to use functional approximations to approximate each of these value functions. And when you have that, you can then start from the very last experiment, the terminal point where we know the GN, that's the KL divergence, and then you can step backwards to the front. So we put Vn here to get point evaluations of Vn minus 1, then we have Vn minus 1 approximated, plug into here to get Vn minus 2, so on and so forth. So that's the backward induction strategy for approaching it. Okay, so as I mentioned before, we saw some good results, but it's very expensive. So we're trying to think, could there be other more computationally friendly approaches to get a good solution to this problem? Okay, and that leads to the new technique we're going to talk about today. The approach we're taking now is that instead of trying to tackle those value functions, we're going to parameterize the policy directly. So all these pi's, we're going to parameterize it with some parameter W. So you can think the policies are now represented as deep neural networks, and the W's are the weights, all the weights of the deep neural networks. And then if we have some good way to approximate the gradient of U with respect to the policy parameters W, then we can plug that gradient into some gradient ascent or stochastic gradient ascent algorithm to try to find a numerical optimal policy in that manner. And that's what we're going to do. So this is known as a policy gradient strategy. And here we're going to look at a actor-critic variant of policy gradient. And what that means is that we're going to build functional approximations to both the actor, which really is the policy. It's the rule in which you take actions, right? So that's the actor, and as well as a critic, which is a value function that is used to criticize or assess how much value you have in performing certain actions under different states. So we're going to do both, making it an actor-critic approach there. It works as follows. At some given policy right now, pi w. So imagine we're doing this optimization loop. So we're at some policy pi w right now. We can then estimate the corresponding value function or action value function, to be specific, or the Q function, to that policy by using Monte Carlo simulations. And that we can do that because we have a model-based setup here. So we can simulate all the remaining trajectories or episodes from that point onwards. And once we have these Monte Carlo approximation at these different points, we can then use a regression approach to build a functional approximation to Q, or Q nu. That's the functional approximation to it. And furthermore, we can also use the Q nu in here to find a lower variance estimate, and that's known as a one-step look-ahead type of approximate strategy there. Right, so at that point then we have the functional approximation to both the policy and also the action value function. Now we can try to derive the policy gradient, the gradient of the objective function U with respect to the policy parameters W. So some math is involved in the derivation, but in the end, we can get a Monte Carlo estimate to this policy gradient that looks as follows. And the key is that we would only need to be able to evaluate the gradient of the policy function with respect to its parameters, right? So that can be done use, let's say, back propagation if it's a deep neural network, and also the gradient of the Q function with respect to one of its arguments. And again, we can also use backprop to do that. Or if it's not neural networks, then we can just derive the gradient using chain rule. So it's doable. That's the key there.
So, Shane, do you think you can finish the presentation in a few minutes?
All right, I'll try to speed up a little bit here. Okay. All right, so I'm going to skip the implementation details and jump to the overall algorithm summary here. So the summary, this is known as a deterministic policy gradient approach for sequential optimal experimental design in the way we're using it. So we would then initialize policy and value functional approximations and enter a loop. We would simulate the episodes to estimate the Q function, and with that we can compute the gradient of the policy to plug it into a gradient ascent update formula there. All right, some quick results. First of all, we did a benchmark problem on a linear Gaussian model. So linear Gaussian model is known to be of a conjugate form. So the posteriors are always going to be analytically Gaussian. So we can actually, if for this case, derive the true solution for this problem. And the overall message is that both the dynamic programming and policy gradient, they can find the optimal policy. But the thing I want to point out is that the policy gradient is orders of magnitude faster compared to the dynamic programming. Now, of course, that's caveat on our implementation, which we don't claim to be the best programmers necessarily. But still, it's a substantial amount of acceleration. So that's very promising there. Then we test this algorithm out into a more complicated physical setting. So here we're looking at a two-dimensional scalar diffusion in a square domain, and where we have a source term, and the source term has this Gaussian-like form, and the center of the source profile is the theta. That's what we're trying to learn, so that we can identify where the theta is, where the source is, and maybe patch it up if there's a leak. And to illustrate the problem, to have a good interpretation of it, we have the source off initially before some time, and it's switched on after that time. So it would be off initially, and after 0.16 seconds now, there's the source and diffusing out. Okay, to build some intuition on what are good designs, here's the expected utility for one experiment design. So the key message I want you to keep in mind is that the best designs are at the corners of a square domain. In the middle, it's the worst, has the lowest utility. And there's a good physical explanation to it. We can discuss maybe offline, but have this intuition in mind. And now we go to the two experiment sequential design, and we set it up such that the first experiment is before the source is on. So we're not going to get any information there. And the second experiment is after the source is on. And we have a mobile sensor that we can move around. We start from the middle of the domain, and then we have some range we can move around. There's also a penalty for movement. You can think as a fuel usage for the vehicle, like a truck that we're driving around there. All right, so here's a side-to-side comparison between SOED and a greedy design, and we can see what happens. So the plots here is just the source strength. Initially, it's off, and the first experiment is happening when it's off. And then the source is on, and then the second experiment happens when it is on. This plot is, or rather, this plot is the physical space where we can see the contaminant plume over time. And here is the belief state. So that's the prior, posterior, etc. So initially we have a uniform prior on where we think the source center is for this plume. The red dot is our sensor location after each experiment, and the source here, star, is the actual source for this particular realization we're demonstrating. So let's see what happens. First experiment, greedy. Let's take a look. It doesn't move. It stays at the center, and it makes sense. It knows that the next upcoming experiment is when the source is still off. We're not going to get any information, so there's no point in moving. We're just going to spend gas, fuel, too, if we want to move. So it stays put, makes sense for a greedy strategy, and the belief state stays the same. SOED, you see it moves towards one of the corners, and it incurs a movement penalty, and it doesn't get any information gain. So it sounds bad, right? But if we look now at the second experiment, now the source is on in the second experiment. Greedy design realizes that, starts heading towards a good corner, the upper right corner, but it can't get all the way there since we have a range constraint and also a movement penalty, right? So it can only get this far, and it gets a reward, cumulative reward of 0.732 here. Now SOED, because we had a head start, it can get much closer to this good corner location, and overall, out of both experiments, cumulatively, the reward is 0.793. So this makes a lot of sense. The SOED, it can plan for the future, look ahead, so that it can make some initial sacrifice so that it positions itself well for an overall much better second measurement, second experiment, and the overall reward is greater than greedy. And we can take a Monte Carlo simulation over all different possible source locations to get these expected reward for SOED, so 0.614, and for greedy, 0.558, and we do see a noticeable advantage of SOED here. And very quickly, we also did this for now including convection. And now the convection speed is also a function of time. So initially it's diffusion dominant, and then the convection comes in to push the whole plume to the right. And similarly, in this more complicated scenario, we also see SOED is having a greater utility than greedy. Okay, so I'm going to just leave the summary slide here, and I do want to acknowledge our sponsors, and I will, if there's any time for questions.
Okay, okay, Shane, thank you so much for the very energetic and interesting topic. I noticed you are the only speaker that stand and keep the talk, which gives us a different energy, so I appreciate that. So let's first ask the audience. Does anyone has any questions that would like to ask our speaker? So I would ask a very quick questions for the time being. I was wondering, so the toy problem about the continuum, the transport, if I understand correctly, is it deterministic? But in the real setup, let's say we have a mechanical test, each time there may be some uncertainty or the specimen are prepared slightly differently. So how to cope with this difference between the experiment that are on a direct numerical simulation environment where there is no source of uncertainty, and the real test where there are some error, some noise, and some inherent difference between different specimens?
Right, so that's a very good question. So in your current setup here, you know, we assume this equation, solving this equation is it fully describes our models. The model is correct, but it could be that there could be some additional uncertain parameters, especially aleatoric type of uncertainty that we cannot reduce from data, in which case we have not considered in this case for the moment, but how I would approach it is also treat that as a random variable, and then all the utility I would take the expectation over those uncertainty as well to try to marginalize it out. So that would be my first attempt to go at that situation.
Okay. Thank you for the question. In the interest of time, I will encourage the audience to switch the discussions to the discussion board. And now we have our grand finale talk given by our co-chair. That actually, I want to take that opportunity to first thank Christian for being a wonderful colleague to help me have to work with us to launch this conference. The success of it is all due to his hard working and responding to all the emails. So thank you very much. So without him, that work that our mechanical check would be very different. So with that in mind, let me introduce our last speaker. So Christian's, I think that we all know him right now. So Professor Christian's Galapetti is actually from University of Michigan, and he's going to talk about a graph theoretical framework for representations, explorations, analysis, and reduce order modeling on computed state of physical system. Thank you. So Christian, you need to unmute.
Okay, are you able to see this?
I see half of the screen right now.
Okay, give me a second here. Good?
Okay. Yes.
Okay, okay. Sorry about that. Okay, hopefully you can still see this. Thank you, Steve. And of course, it's totally untrue. Steve honestly did definitely the majority of the work. But anyway, we're all glad that you're here. Thanks for staying till the end. I know it's 5 o'clock on the east in the Eastern zone, so I won't keep you too long. But I'm very excited to share some of these ideas that we've been developing over the past about a couple of years on using graph theory to really look at computed states of physical systems in a different way. I'm going to give a broad perspective of several aspects of this work. And as you can see in the title itself, it's a long title, and Steve took the trouble to read it all. We're talking about representation, exploration, analysis, as well as reduced order modeling, right? So I'll try to step through these. Of course, I'll acknowledge the people who've done all the work. Matt Duchesne is a grad student who's doing whose PhD dissertation this is part of. Xiaoshuan Zhang and Greg Tykert also contributed to it, as did other people in the group. Okay, so let's start with this slide. The origins of graph theory is supposed to go back to Leonhard Euler, and the legend is that in the town of Königsberg, which was then in Prussia, there was a sport among the nobility in the city to try and traverse these 4 different enclaves of the city by using the 7 bridges. And the sport of it came about by them trying to do it by traversing each bridge only once. As it turned out, Euler ended the sport when he showed that it could not be done. And these are commonly pointed to be the beginnings of graph theory. And essentially, Euler showed that you could not construct such a path as the nobles were trying to take. Essentially, he demonstrated that you could not construct what came to be called an Eulerian path on graphs. Since then, of course, graph theory has expanded tremendously. It's widely used in many engineering applications, and I've listed some of them here in the first few bullet points, and these are commonly known. I will say, though, that the use of graph theory in PDE-based computational physics is somewhat lesser widespread. There is some work in computational fluid dynamics. There's work looking at interactions of vortices and looking at each vortex as a vertex on a graph and the interactions between them as defining edges. There's also work done by Steve here where he and his group have looked at how information flow in a computational model, quantities and relations between them can be treated in a graphical framework. And he's also combined that with game theory to come up with new constitutive relations. The approach we have been trying to take is the following, okay? So we all know how to compute solutions to PDEs, to initial and boundary value problems. And of course, scientific computing and computational science have taken this to a high art. We're able to solve very high dimensional problems, often of the order of hundreds of millions of degrees of freedom, billion degrees of freedom is no problem. And the way we regard this is that in general, these are nonlinear solutions, schemes that we're applying, nonlinear solution schemes that we're applying. We're looking for some solution U, and it's parameterized by some parameter set P. Now, though we solve such high dimensional problems, often in engineering, design, and decision making, what is of true interest are low dimensional vectors, which are typically quantities of interest. And these we will call states of the system. They're typically functionals on this high dimensional solution U. Some of these examples are listed on the next bullet point here. We have lift drag, failure load, fracture energy, charge capacity, magnetic moment, total free energy, all these kinds of things, right? These are quantities you extract after solving a potentially high dimensional problem. And then, and these define states. Now, we can talk about transitions between states, and we label them as T. So we look at a transition Tij as going from state J to state I. And this now can be viewed as either a numerical solution step, or it could be some physical property that changes in going from state J to state I. So when we have all of these states can be collected together, and those define the vertices. The transitions between them define edges. Okay, so you put all of this together, and you can now look at each sort of computational computational campaign for a particular problem as generating a graph. I've shown this here schematically. These are solutions obtained by, it could be linear or nonlinear quasi-static elasticity. Each of these states now is labeled as J, I, K, L, and so on. I've shown here to the right the very well-known, well-recognized equation. It's just the linear balance of momentum equation with some boundary conditions on it. Now, each state that we compute for the system is obtained for some parameter set P and boundary conditions, right? Now, and I've labeled these states here as S. A linear or nonlinear solution step then is a transition or between any of these two states. It could also involve some change in a transition quantity. And later on, I will indicate what these transition quantities can be. So if you put all these states together and the transitions between them, we construct a graph as consisting of these vertices and edges, as I described earlier. The vertices come from the states, the edges come from the transitions. Now, this graph is connected if every state can be reached from some other state along some edge, T. Okay, it's unconnected if there is some state which just cannot, if there is some state from which you cannot go to another state or which cannot be reached from another state. Okay, and so now we see that we're coming up. We observe that the ability to solve these problems also leads to notions on graphs, right? Notions of connectedness or disconnected states. Because we're dealing here with, if you're thinking about this as linear or nonlinear elasticity, these are non-dissipative systems. It turns out that if you can go from a state J to I, you can also go from I to J, okay? And likewise, in terms of transitions, you can go back and forth between I and J. What this means is that linear non-dissipative boundary value problems are represented by what are called undirected graphs. And that's indicated by the fact that these edges do not have arrows in them. You can go back and forth. Okay. Furthermore, if it turns out that you can attain every state from every other state, as again shown in this schematic, for instance, state I can be reached from every other state, and that's true of all the other states, then we have what is called a clique. This is typical of linear non-dissipative boundary value problems. Again, think elasticity. Finally, one can give these notions of weights on edges, which can be defined in a number of different ways. Often in computational physics problems, it's relevant to define it to be some function of the difference between these states, right? Maybe some function of the Euclidean norm between these states. So this is just a sort of primer, right? Sort of a sampler on how one can start thinking of computed solutions as essentially inducing a graph. So we've applied this to a number of problems. I'll step through some of them, continuing to demonstrate how we can use graphs to represent, explore, and analyze these computed states on physical systems. So the images you see here are microstructures that we've computed on a system of non-convex elasticity. We've written quite a few papers on this work, and it involves martensitic transformations, as I mentioned, non-convex elasticity, the formation of these microstructures, laminae, and so on. It's a very rich theory. Now, what we have done from there is, as you could see, all these microstructures tend to be periodic. What is of interest in an engineering setting, in a materials modeling setting, is yes, these microstructures are of interest, but it is equally of interest to also know what is the homogeneous response of these structures. So we went about doing these kinds of problems where we would take the unit cell of one of these structures and subject it to a number of strains. These strains are denoted here as E. And each strain state that we applied on one of these microstructures, on one of these unit cells, leads to a state that I denote here as SI. You collect, and you can apply different, I've shown you just one sort of shear strain state here. You can apply different strain states, and you collect them together to define vertices, right? So now you start collecting all these vertices. Now we go to this graphical representation where each of these red dots here represents a vertex, which actually represents a certain homogenized strain state applied on this sort of, on this unit cell. And then if it turns out that from one of these states you can go to another, like from this strain state, if you can go to another, it means that you have a transition between two strain states, between strain states J and I, that leads to a transition between them. Now you see on this graph, some of these vertices are unconnected, whereas others are connected by the fact that there are edges between them. It turned out that maybe one of these red dots, which is connected to another one, we could go back and forth between them by doing these, by essentially through our nonlinear solver. In this case, you see that some of the vertices were unconnected because I'm showing you the graph in the process of it being constructed. So we may have sampled some strain state, but not have tried to get to another strain state from it, right? So as you sample more of these transitions, you would start filling out this graph. One can do an analysis on this. How does one go about doing an analysis? One can define what is called an adjacency matrix, which depends upon the weights. An adjacency matrix has an entry which is equal to the weight. If there is an edge between two vertices, it's equal to 0. Otherwise, one can do a diagonalization to come up with this diagonal matrix, and you can put them together to come up with what is called the graph Laplacian. It is, of course, closely related to the Laplacian that we know from other discretization techniques applied to elliptic problems, for instance. From this graph Laplacian, one can then construct an energy where the x here corresponds to the positions of each vertex on a planar graph. And then one can seek to minimize this energy. When one does that, one gets a very pleasing layout for this graph. It's a planar layout, and it's shown on the right here. It's called the Kamada-Kawai layout, and it's obtained by minimizing this energy I showed you here. One can do further analysis on this, which comes from the adjacency matrix. One can come up with many notions of what is called centrality of these vertices. And centrality of a vertex, there are many notions of centrality, but they all tell us something about how connected each vertex is in the graph and how important it is to the whole graph. In this context, each of these vertices, remember, represents a strain state. In fact, the size of the vertex here is the magnitude of the strain. This is the green Lagrange strain that we applied on them. And then the edges tell us which vertices which strain state we could get to from which other strain state. These vertices have been colored by what is called the eigenvector centrality, which is one of these measures of centrality. The colder colors indicate vertices or strain states which were reached from fewer other strain states. The hotter colors indicate strain states that could be attained from many other strain states. And now here we see something interesting, right? So some of these large strain states, which actually correspond to large strains, can be attained from many other strain states, right? They have a bright red eigenvector centrality as this one that I'm pointing out here. I think that's 32, strain state number 32. On the other hand, a relatively smaller strain state with a smaller Euclidean norm of the strain, sorry, Frobenius norm of the strain, could be attained from fewer strain states. So this now begins to tell us that there's some effect of the microstructure here, which makes certain strain states attainable from others, but maybe not certain other strain states. It's related to the microstructure, to your nonlinear solver, the nonlinearity of the problem, the non-convexity, and all of this, right? There are other ways in which one can analyze this graph as well. There are other layouts. In here, I'm showing you what is called a spectral layout. It is the same graph, but now shown on an eigenspace that is defined by the eigenvectors of the two vertices which have the lowest connections to other states, to other strain states. In particular, it is these two strain states that you see here in blue, at sort of at the corners of this graph here, and those are strain states 114 and 21. And I've just shown you what those strains actually, what the strain values actually are. So as you can imagine, now you can start doing other types of analysis. You can see which strain states are available from whether there are sets of strain states that are accessible from all others. That would lead to the notion of a clique. or that's a subgraph where all the states are attainable from others. One can look at traversal to see which strain states you can sort of traverse through to get to other states and so on. Right, all of this gives you some idea of what your physical problem is doing, what these microstructures are like. So I'll take kind of a timeout for one slide to just state what we learned from this, right? We see that properties of solutions to PDEs can be placed in correspondence with graph theory. There are these physical properties and numerical schemes which induce correspondences. I talked about how these states can be written as, can be collected into vertices. Transitions can be collected into edges. I will also state that, I will also say that some of the correspondences, which I referred to above, lead to definitions in graph theory. So one can induce new notions in graph theory. Others turn out actually to be theorems or corollaries that already existed in graph theory, but find correspondences in our computational physics problems. This work appeared last year in Computer Methods and sort of summarized all these ideas. How am I doing on time? I want to make sure that I have time enough. Okay, so I'm going to take the next 4 or 5 slides to also show some other problems that we did in the same vein. We've looked at dissipative dynamical systems, unlike that problem, which was elasticity and which is conservative, right? Schematically, I've shown you the graph that I could generate by looking at problems of cell division and growth through a phase field model. Now, phase field models we know are dissipative, right? I've written out on the right-hand side here a first-ordered dynamical system, dissipative dynamical system. Sigma here is the flux, U is the solution, and so on, with some boundary conditions and also initial conditions in this case. For these kinds of problems, the states can be parameterized by the time, and the transition represents the time step between 2 states. So if you'd done the sort of a phase field problem to look at cell growth, you would have started out with some state. You could have gone to 2 other states, depending upon which direction you decided to go to, and so on and so forth. The important thing is that because these are dissipative systems, like through phase field descriptions, we lose time reversal symmetry, which means that you can go from a state maybe SI1 to SJ1, but you cannot go back. It also means that these transitions or the edges are directed, right? So we get directed graphs. Also, it means that if you have a state such as here, which is at a later time than some other state, like SL1 is later, as it's at a later time than SI1, you cannot reconnect L1 to I1 directly. This means that you cannot get graphs that are clicks, and click graphs are ones where every state is connected to every other. You cannot get that in a dissipative system. It also means that periodic orbits are not allowed. You have only acyclic graphs, no Eulerian paths, and so on. In order to actually see these properties reflected in a graph, as you generate these graphs by doing the solutions, we have to define what are called entropy quantities, which are simply functionals of the solution, which are either always non-negative or non-positive. So the next bullet point just says that you've got to define these entropy quantities. The final other property that one can get is all the graphs that emerge from these dissipative systems are trees, which means that if you want to get to a certain state L1, there's only one path that's going to get you to it. There is no other path that can get you to that, which also is reflected in dissipative dynamical systems because all these systems are path dependent, right? So we see this correspondence also emerging. So we've applied this to a problem that we had actually done before we even thought about graphs. In a paper that appeared in 2018, we had applied machine learning methods in materials physics to essentially replace phase field dynamics with surrogate optimization and multi-fidelity algorithms to predict precipitate morphology. So you're seeing just a few of these precipitate states that we had, precipitate morphologies that we had explored. I'm showing you just 12 out of a very large number of these morphologies that we had explored. And then we used surrogate optimization and multi-fidelity algorithms to navigate the landscape or the free energy landscape implied by these precipitate morphologies. This was for precipitates in magnesium yttrium. You're seeing on the right-hand side here the free energy as you cycle through, as you go down through these 12 states. There's no cycling; the energy is just decreasing in this case. So this work was done before we thought about graphs, but then we realized later on that each of these states that you're seeing here could actually be put on a graph. We did that with all the data that we had sampled for this problem, and you get a graph as shown here. This too is a tree graph. I'll say something more about it. Each vertex here represents one of those precipitate morphologies I showed you on the previous slide, and you saw the GIF movie, GIF cycling through it. You also observe that we have edges between them, and you observe that these edges have arrows. They are directed edges. We could define these edges by using defining notions of chemical potentials obtained from the free energies of these systems, and then looking at also using invoking a maximum dissipation postulate on top of it. Finally, we could also induce a notion of time on this graph. By also using the insight that these kinds of problems are driven by Allen-Kahn type dynamics and so on. Now, the advantage of representing this whole system on a graph such as this is that we are able to represent many, many distinct paths. Whereas when one does use a phase field model to look at the same problem, one can take maybe only one of these paths. I mentioned that we could induce this notion of a graph time of transition between two states. Having defined that, one can also look then at what are what is the time it takes, what is the graph time it takes to actually transit one of these paths. The 5 paths shown here in red are the 5 slowest paths available. The slowest path of them all is this one that starts at state 1174, right? It starts here, navigates through here, and ends up at this root. This root, by the way, is the lowest free energy state of this whole system. And this particular path starting with 1174, ending in this low energy state, is shown here in terms of transitions between all these configurations of these precipitates. So one can do this. One can also do many other things. One can look at the steepness of these paths. One can also look at how they're connected, how all these states are connected, using other notions of centrality. In this case, we use the notion of page rank, which is very much used in ranking websites. And it had a relevance to this particular problem. Moving forward, we've also done this to other problems. We've also applied these ideas to other problems of microstructure evolution. What I'm showing you here is another 2D calculation with a problem of this problem of non-convex elasticity, where you also have a phase field imposed on top of it. On the left, you're seeing here the blue is what is called a square phase of this material. In red, you're seeing a rectangular phase. The rectangular phase itself has 2 different strains, which is shown on the right here. So we've done these calculations, and our intention in doing these calculations was to then extract homogenized responses for these microstructures. When we were looking at those homogenized responses, we've developed multi-resolution neural networks in order to represent the energy as well as the free energy as well as the constitutive response of these effective microstructures, right? So now we've developed these methods as indicated in the citation to this paper above here to come up with what are now homogenized stress strain constitutive relations for these types of microstructures. The plots here below show you on the left the change in free energy as one cycles through these microstructures. And on the right here, we see the strain energy of any one of these microstructures as it is subjected to many different strain states. Again,
so we may need to wrap up pretty soon. So
sorry. Okay. How much time do you think I have left?
I think we maybe another 4 minutes. Do you think
sure.
That is
no problem. Yeah. Okay. Sounds good. Okay, so again, one can put all these microstructures on a graph, right? So the backbone of this graph represents the change in free energy as one is going through time, as these microstructures are changing. Each of these subgraphs going off the main backbone represents the sampling of these strain states. And the coloring here is again by eigenvector centrality. So again, one can put these states on a graph such as this. So far, I've shown you only ways in which one can use graphs to represent and explore, maybe do some analysis of these physical systems, right? What about reduced order models? This is the last idea I'm going to present here, and there's a lot of detail in this, but of course, I'm giving you a sort of broad perspective of this sort of sweep through graph theory, so I will keep this also high level. It turns out that one can use a non-local calculus on finite weighted graphs to actually compute to compute on a graph such as this, okay, using these sort of relations that I put out here. In this case, U would be a quantity such as the free energy of one of these microstructures, and X would be attributes of these microstructures. In this case, it would be things like phase volume fractions, the average strain on the microstructure, and so on. One can define a gradient on this graph, where remember now the gradient that I'm taking is not with respect to space, but with respect to these attributes of these states of the graph, right? With respect to phase volume fraction, strain, and so on. One can define a dot product. There are inner products. There's a divergence theorem. You can define a divergence, the divergence theorem. One can come up with adjointness properties and so on. What's most important to us is that one can then define these, one can actually even define partial derivatives of these quantities. So now on this graph, such as here, I can talk of the partial derivative of the free energy with respect to phase volume fraction or with respect to average strain. What is that used for? Well, if one can talk about these kinds of derivatives, one can then start constructing functional representations. And in particular, we've been exploring with Taylor series functional representations of the free energy and other quantities, as well as writing out PDEs. What I'm showing you here on the right-hand side is a model for the free energy computed with respect to phase volume fraction, strain energy, and so on. The representation we arrive at is a Taylor series representation. And now one may ask, why do you need a Taylor series representation? What other representations could one have? One could have neural networks, but the nice thing with this sort of approach is that it gives a certain amount of interpretability, right? You can actually see a Taylor series and you can understand and query this representation. We've done this also to other problems. I know I'm running out of time, so I won't get into great details here. We've done this for nuclear reactor fission, nuclear reactor cross sections. Nuclear reactor computations are very complex, multi-physics, multi-scale efforts going from quantum mechanics through neutron flux calculations to diffusion calculations and so on. Shown here is a schematic of a nuclear reactor showing this exploded multi-scale view. At the end of it all, what nuclear engineers are interested in is how does something, a quantity like these cross sections, change with respect to macroscopic parameters of the nuclear reactor, with respect to moderated temperature, moderated density, fuel temperature, and so on. We've used this approach to also develop Taylor series representations of how these fission cross sections change with respect to a number of these macroscopic nuclear reactor properties. This is available as a preprint. Finally, we've applied this also to looking at the seismic response of buildings. These are sort of larger scale computational calculations shown top views, showing you various collapsed states of buildings. You can see actual pictures of buildings that have collapsed and computed states from high fidelity calculations that correspond to these collapsed structures. What we extract from these computations is something called the interstory drift ratio. You can see this building seems to have sheared. That's related to this quantity called the interstory drift ratio. We've related it to quantities such as the displacement, velocity, acceleration, as well as intensities. And finally, the derivative of this interstory drift ratio with respect to the intensity. We've used insights into the way these drift ratios evolve as these buildings are seismically loaded to write out and actually extract from these high fidelity computations ODEs for the evolution of these drift ratios subject to all these quantities. Also obtained by putting all these states on graphs and then doing these computations with this non-local calculus. Okay, that's it. To summarize, I've talked about how one can use graph theory for representation, exploration, and analysis of large-scale systems. I showed you a few examples from non-convex elasticity through a couple of dissipative dynamical systems. That work appeared a couple of years ago, actually last year, sorry. And then towards the end, I talked about these reduced order models. Currently, our focus is on developing reduced order models for other types of physics problems, also using this non-local calculus. There is a preprint available, but the more detailed work is forthcoming. So, okay, that's where I am. Thanks very much. I'll keep my screen share up just in case there are questions.
Okay, so thank you, Christian, for the wonderful talk and for the leadership for this conference. So let me repeat one of the audience questions. So for the string state example, how do you define the distance between vertex? Were you using the matrix norm of the string tensor? Or?
Yeah, exactly. This is just the Frobenius norm of the strain tensor, but it's the strain tensor applied to this unit cell, and this is critical. It's like the homogenized or the average strain tensor, right?
Yeah.
And that is important because really what we're seeking to do is what led to the state, or what led to one of these microstructures. Sorry, I'm going the wrong way here. What led to one of these microstructures is a very detailed high fidelity computation. But rather than be driven by only use that high fidelity state, that high dimensional state, we know that in engineering design, what we're interested in is saying, oh, but I don't care about that. If I have this unit cell, I really care about only the average strain state on this, right? So that's what we've used here.
Yeah, I see. I was also wondering in this problem, this is something maybe I don't understand correctly, is that shouldn't we get actually a complete graph where every node is visited by another node? Because you can always
absolutely
gradient, right? So
yeah, absolutely, right. So usually yes, but what happens is that we are taking these data from a computational solution, right? And so now depending upon your right, so yeah, depending upon the nonlinearity, the microstructure, your solver may not converge. So that is what I'm reflecting here. Because that's where I'm getting my data from. Absolutely, yeah. So, but within this, there is a clique. I didn't show it here, but the clique, I have it on a later slide. There is a clique which is of size 34 here. Let me see if I can get to showing you. Yeah, here we go. Yeah, actually here, the red vertices represent the clique here within this graph. Those are the states which are all attainable from everyone else. But the blue ones do not have that complete connection.
I was wondering, do you think it is also possible that if we know what is the coordinate in the graph, if we know how to connect a new nodes, but we don't want to run the simulation, is it possible to using it as a regression tools?
Absolutely, yeah. And that's the point, right? So having developed this, now you can develop a reduced order model just like the other ones that we were talking about that I presented, which then represents sort of the average behavior of these microstructures, right? And what you can now use this to construct a reduced order model for the behavior of this microstructure and others. Absolutely, yeah.
Okay. Yeah, sorry. Yeah. So I also have another questions about the reduced order modeling part on the graph. So if I don't understand correctly, the solution is compute on the nodes of the graph right now in that model. Maybe I don't. But I was wondering you mentioned that in the graph, we can build a gradient, partial derivative, and all the entity that are in the Euclidean space or in other space. So is there a way that we can compute in the graph and then map it back into the Euclidean space in some means?
So not so clear. So it turns out that so first of all, these attributes, right, on this slide, for instance, the attributes X would be whatever you put into your graph, right? Some of them may be, maybe the first component of this vector, X is a vector actually. The first component may be phase volume fraction. The next thing may be some strain state. Third maybe some interface length or something like that. So whereas one would have to do a normalization for all of that. And then one can map them onto a Euclidean space. One can represent them as a Euclidean space after some suitable normalization. But they're not the same as physical. They're not physical space, right?
So yeah, okay.
Yeah.
I see. So, okay, so I think we are running out of time.
Yeah, of course. Yeah. We have run out of time. Sorry.
But I think, but I enjoy. I mean, I think we enjoy the discussions, and I want to thank all the audience and all the speakers once again. Thank you so much. We still have the closing keynote that are a little bit. We are a little bit late right now, but maybe we can still catch the last part of it. So thank you very much. In particular, the Christians again. I hope we will see each other very soon. Thank you. Bye.
Definitely. Thanks, everyone.
Thank you. Bye.